Can you hear me?
Oh, yes. Hi, Javier. We can hear you.
Good afternoon in Sweden and in Europe in general. We have an audience also in other countries here in Europe. And good morning in Bolivia. My name is Javier Linares Pastén, and I will be the chairperson in this session. Welcome everybody to the public defense of the doctoral thesis of Alvaro Gutierrez Rojas, entitled Optimization of the Sensor Chip Surface in a Capacitive Biosensor for Use in Aflatoxinas Assays. I would like to start introducing the opponent, Professor Lohman Usum. Dr. Usum is a professor of biochemistry at the Department of Chemistry, Faculty of Science, Hacettepe University, Ankara, Turkey. His research interest mainly covers polymer science, surface modification, characterization, biochromatography, biomaterials, and especially biosensors, which make him a suitable opponent for Alvaro's thesis. Most welcome.
Thank you.
The members of the examination committee are Dr. Leonard Stoika, who is present here in Lund. Dr. Stoika received his PhD title at Lund University. Currently, he's a project manager for conductive polymer coatings at Heraus Medical Components, Hanau, Germany. His interest is in electrified interfaces, biosensors, electrodialysis, catalysis, and characterization of novel enzymes, covering from concept proof to commercialized products. Most welcome. Dr. Sylvester Gaspar. Dr. Gaspar is a senior researcher at the International Center of Biodynamics in Bucharest, Romania. He was a research engineer at the Department of Analytical Chemistry at Lund University. After he obtained his PhD at the Department of Biotechnology from Lund University. His current research focused on developing biocatalytic micromotors, micropumps, and electrochemical biosensors. Most welcome.
Thank you. Nice to see everybody.
Associate Professor Peter Spegel. It's also present via Zoom. His background is in analytical chemistry, then 12 years in medicine, and back in analytical chemistry again. His main interest is in using mass spectrometry to study metabolic regulation in response to metabolic diseases and complex samples in general. Most welcome.
Thank you.
And Dr. Jaime Castillo León, present also here in Lund. He is a head of product design and development of Spermosense AV Lund, Sweden. His background is in chemistry, Universidad Industrial de Santander. He received his PhD from Lund University in electrochemical biosensors. His experience is in building and leading multicultural teams in the development of nanotechnology-related products and solutions for the biosensing and solar energy industry. Most welcome.
Thank you.
The doctoral thesis supervisors are Martin Herstrom, main supervisor, and Bo Mathiasson, assistant supervisor. In Bolivia, we have as assistant chairperson, Carla Crespo. Carla, please introduce the Bolivian staff.
Thank you, Javier. Good morning and good afternoon, ladies and gentlemen. Welcome to this doctoral presentation. I'm very pleased to be here today, as this is my first opportunity to present a real-time PhD defense from Universidad Mayor de San Andrés, located at La Paz, Bolivia, UMSA. As you know, in this opportunity, it is presented the examination process for the thesis, optimization of the sensor chip surface in capacitive biosensor for the use of aflatoxin assays by Alvaro Gutierrez Rojas, doctorand from the sandwich program between Bolivia and Sweden, under the support of the Swedish International Development Cooperation Agency, SIDA. I acknowledge here the presence of Maria Eugenia Garcia, our Vice Rector of UMSA, Mauro Costantino, Director of the Department of Research, Graduate and Social Interaction, DIPGIS, Ignacio Chirico, Coordinator of SIDA at UMSA, Walter Montaño, Dean of our Faculty of Pharmaceutical and Biochemical Sciences, Alberto Jimenez, Co-Supervisor of Alvaro in Bolivia, Maria Teresa Álvarez, Coordinator of Sub-Program, researchers, friends, and colleagues from La Paz. And of course, to you supervisors, opponents, committee, researchers, and colleagues from the Division of Biotechnology at Lund University. For us, this event is very special because it closes a phase with the Swedish cooperation in Bolivia and shows the achievements. Therefore, I hand over the microphone to Alvaro for the presentation.
No sé, pues quiero apuntarlo. No quiere eso. Okay, hello everyone. My name is Alvaro Gutierrez, and I will present my thesis entitled Optimization of the Sensor Chip Surface in a Capacitive Biosensor for Use in Aflatoxinas eye. As Javier said before, my supervisors in Sweden are Martin Hedstrom and Bud Mathiasson, and here Alberto Jimenez. First, I will start with the outline, starting with the introduction. Then I will go through the biosensors. Then I will go deeper to the Capacitive Biosensor, the setup of the system, the main results, and finally, I will end with the conclusions. As introduction, we are going to talk about mycotoxins. These mycotoxins are secondary metabolites which are known as low molecular weight molecules. These molecules are less than 700 Daltons, which are pretty small. And between those, we have many of these mycotoxins. Between these mycotoxins, we have aflatoxins, ochratoxins, phimosin, trichotresins, patulin, and serralenone. These aflatoxins can stay in different matrices, like in the case of aflatoxins will be in peanuts, maize, ochratoxin cereals, coffee, phimosins maize, trichotresins grains, patulin apples, serralenone corn. And these are characterized principally for the toxic effect that this has. This toxic effect can deal to trigger a cancer in humans. So for this case, mainly is aflatoxins, fumosin, and patulin who can develop this cancer. Different kind of fungal species are present here to produce these mycotoxins, as is the case of aflatoxin, that is the case of study in this thesis. This aflatoxin is a natural contaminant, and these are produced for Aspergillus flavus and Aspergillus parasiticus. The name of this aflatoxin came by Aspergillus flavus. For that reason, it's named aflatoxin. These are toxic compounds, and these can have four main molecules, which are the B1, B2, G1, and G2. The B1 and D2 molecules are characterized for the blue color present under UV light, and in the case of G1 and G2, the green color under UV light also. The most toxic aflatoxin present in this study is aflatoxin B1, as this can have an effect of hepatotoxic and carcinogenic effect. This aflatoxin can form adducts with the residues of guanine in the sequence of DNA, as can be seen here. As this aflatoxin has high affinity for nucleic acid. One important thing in here is the permit levels for aflatoxins. As the foodstuff in the foodstuff that is present, these aflatoxins are tree nuts, oilseed, cereals, and even milk. And the concentrations go in a round of micrograms per kilogram. So this is the main characteristic that we need a really good method to realize the detection for this aflatoxin. And as this can be accumulated, the LD50 for humans is 0.36 milligrams per kilogram. Then we need to know how to detect this aflatoxin. And for the detection, conventional methods for aflatoxin detection can be TLC, capillary electrophoresis, HPLC, and ELISA. Mainly used HPLC and ELISA for this detection in different countries. These methods has some advantages and then also have some disadvantages. Between the advantages for HPLC can be the fast, accurate results, and in the case of ELISA, that the large number of samples can be analyzed. But the disadvantages in the case of ELISA is the washing steps, and HPLC, the rigorous sample purification, training personnel, and this is also expensive. So for this reason, we are going to go inside the biosensor, and UPAC defined a biosensor as a self-contained integrated device which is capable of providing specific quantitative or semi-quantitative analytical information using a biological recognition element which is in direct spatial contact with the transducer element. The biosensor has these parts. The first part is the bioreceptor, followed by the transducer, then the electronics, which is the amplifier and the processor, and finally the display where the result will be shown. These bioreceptors can be antibodies, enzymes, cells, aptamers, nanoparticles. In this case, we are going to use bioimprinting and also molecularly imprinted polymers. When the analyte binds the bioreceptor, a chemical signal is produced, and this chemical signal needs to be transduced to an electrical signal. This electrical signal then will be displayed in the screen. In order to see these characteristics for the biosensor, we have different kind of electrochemical, different transducers, in which we have the electrochemical, optical, thermal, electronic, parametric, and acoustic. The main focus are the electrochemical sensors, as we are going to use a capacitive biosensor which belongs to this group. The principle of the capacitive biosensor is based on the dielectric properties we has, as can be seen in this figure. But we have the compact layer with the inner Helmholtz plane and outer Helmholtz plane, the diffuse layer, and the bulk solution. The characteristic for this capacitive biosensor is the sensitivity, real-time measuring, label-free, and reduced sample preparation. In order to measure the total capacitance from the sensor, we are going to have different layers for this setup. So we have the capacitance for the insulating layer, which is this one, the biorecognition element, that can be the antibody, the bioimprinting, and so on, the antigen, which binds to the biorecognition element, and the capacitance of the double layer. As we can see, everything is 1 over the capacitance. So the lowest capacitance is dominating the total capacitance, and this must be given by the antigen. And also, when we have the insulating layer, this must be as high as possible in order to have the domination of the capacitance for the antigen. In order to realize the insulation of the electrode, we are going to use self-assembled monolayers. Those are tiny molecules which are forming films and spontaneously formed. As is the case from here, we are using thiourea and thiotic acid. Another way to realize this is to realize the electropolymerization. This electropolymerization uses tyramine, where we have this kind of plot where the oxidation current present in here is going to decrease and the oligomer size is going to increase. When we are using alkaline solutions for this electropolymerization, this can be a self-limited growth from the tyramine. So we are going to have just a certain number of layers, and then the polymerization will stop. One of the molecules that we are using for the biorecognition is the bioimprinting. We were using albumin and ovalbumin, but we have seen that the albumin has a lot of hydrophobic amino acids. So it's better to use ovalbumin. In the case of ovalbumin, we realized the denaturation as the first step to get a denatured ovalbumin. Then we added the aflatoxin, that is our target molecule. Then we added a glutaraldehyde compound molecule in order to realize binding between inside the protein. This in alkaline conditions. Afterwards, we realized the dialysis in order to release the aflatoxins and had the imprinted protein ready to use. Another way to have pockets for aflatoxin detection is to use molecularly imprinted polymers. In the case of molecularly imprinted polymers, we use mercaptobenzene imidazole as main molecule, as the monomer. Here we use electropolymerization, and this electropolymerization was realized over the electrode and the formation of disulfide bonds between these monomers. And as we can see in here, in every cycle that we are realizing by cyclic voltammetry, the elongation of the polymer is set. We must emphasize in here that this molecularly imprinted polymer is acting as the insulating layer and also as the biorecognition element. Another way to increase the surface area for the detection of the aflatoxins were the use of gold nanoparticles. These gold nanoparticles are characterized to have negative charges caused by the citrate compound. And we are using glutaraldehyde in order to generate gold net formation. The configurations that can have this glutaraldehyde, this dithiotetraethyl, sorry, is standing up, lying down, and forming bridges between gold nanoparticles. But as I said before, the negative charges between these gold nanoparticles must be reduced. So we are going to use sodium chloride to decrease this repulsion between these gold nanoparticles and get a net formation. So in here we can see the gold electrode without the formation of gold nanoparticles, net formation. And here we can see the net formation of the gold nanoparticles with dithiotetraethyl. The importance for this study is to develop a sensitive technique to guarantee that concentrations are below the permissible level as it was shown before. We are using a capacitive biosensor based on current pulse method. The setup for this system consists in two valves. The first one has 3 ports and the second one has 9 ports. In the first one, we have the pump, which is going to give us a constant volume of the carrier buffer, which is in the port number 2. When we are initializing this system, the waste, the excess of carrier buffer will go to the waste. Then when this system is realized and is starting, the carrier buffer will go until the port number 0. In this second port, we have in the number 1, the regeneration solution. We can use 6 standards or 6 samples. We have the waste, and then the most important part where we are going to the flow cell. Before going to the flow cell, this by the system, this must be degassed as the gas can affect the measurement of the capacitance. In this flow cell is based on 3 electrodes. The working electrode with our insulating layer and our biorecognition element is on. the auxiliary electrode, and the reference electrode. And finally, when the detection occurs, then it goes to the waste. As the main results, we were realizing a surface cleaning method, and we wanted to decrease the different solutions used and the steps in order to have a less steps cleaning method to realize all the detections. We realized it in the first part, the normal way to realize the cleaning method, that is using acetone sonication, ethanol sonication, pyranose solution, and then plasma cleaner. And in the second one, it was using acetone sonication and ethanol sonication. As these electrodes are new, so just necessary to use acetone and sonicate or ethanol. And this has been confirmed when the cyclic voltammetry using permeable redox coupled of ferrocyanide can react in here, where we have the anodic peak current where the oxidation occurs and the cathodic peak current. We can see that the difference between A and B is not so significant, so we opted to use the second method for cleaning electrode surface. As I said before, we are using a permeable redox couple, which is ferrocyanide and ferricyanide. The oxidations occur here in this part, where we have a positive current, and the reductions occur in the lower part. As I said before, the electrode in this part shows a clean electrode, so we don't have anything over the electrode. When we are realizing the insulation, we use thioptic acid, thiourea, or even electropolymerization of tyramine. We can see that it's reducing the degree of the permeable redox couple here. And then every time that we are adding different components on the layer, as the printed protein or antibody, and finally using 1-decaintiol in order to fill the pinholes, we are going to have a more flat figure. A normal biosensing for this type of sensor starts with a regeneration, where we are going to release all the molecules that could be attached on the antibody. Then the aflatoxin will be injected, and this will bind to the antibody or the biorecognition element who is in here. Finally, we are going to realize one more regeneration, and we will release the aflatoxin. As can be seen here, when we inject the aflatoxin, the change in capacitance can be noticed, and this will be given a value which is in an order of picofarads in this case. When we were realizing the first paper, the best results came with tyramine. In the case of tyramine, we used two methods for electropolymerization. The first one was methanol with sodium hydroxide, and the second one, using phosphate buffer with ethanol. In the first method, we can see that have a linear range to 10 to minus 7 to 10 to minus 13. And in the second method, to 10 to minus 7 to 10 to minus 9. So we can see that when using methanol NaOH, we have a linear range and a value lower in here. This is, as we said before, by the self-limit growing that this electropolymerization will have. So the gold nanoparticles over this tyramine will be will give us some a large surface area. Another way to have our biorecognition element is bioimprinting. We have seen that when using bioimprinting, we need to have one molecule that is the bioimprinted protein when the target analyte is set up with the aflatoxin with the printed protein and the non-imprinted protein. And in this figure, we can see that there is some kind of non-interaction, non-specific with the non-imprinted polymer. We realized that the measurement of aflatoxin B1 in certain concentration, also with the same concentration for T2, toxin, serralanone, and DON, and we have seen that there is some unspecific interaction, but this is not so, it's not high compared with the main measurement that we are realizing for aflatoxin. In the case of molecularly imprinted polymers, we have also one molecularly imprinted polymer, which is synthesized in the presence of aflatoxin, and the non-imprinted polymer that is without the presence of the aflatoxin. We can see that there is no specific interaction, as can be seen in the red line, and the pockets are specific for aflatoxin. In this case, the molecular imprinted polymers has a repeatability response until 40 cycles, which is really high. So it's a good option to use it for the measurement in a capacitive biosensor. When using gold nanoparticles, we have seen that the best option of sodium chloride concentration in order to reduce the repulsion between gold nanoparticles is the concentration of 250 millimolar, with a percentage of absorption of antibody of 57.7%. As we can see in the linear range, we have 10 to minus 7 to 10 to minus 13, which is the same as when we are using electropolymerization of tyramine. In paper 1, we can see that the linear range is 10 to minus 7, 10 to minus 13, having a reusability of 25 cycles when using electropolymerization of tyramine. In paper 2, we have a linear range of 10 to minus 6 to 10 to minus 9, with a reusability of 32 cycles, this for bioimprinting of aflatoxin in oval booming. The paper 3 was 10 to minus 6 to 10 to minus 10, with a reusability of 40 cycles when using electropolymerization of molecular imprinted polymers and non-imprinted polymers. And in paper 4, 10 to minus 7 to 10 to minus 13, with a reusability of 25 cycles when using gold nanoparticles for net formation. We can see that the reusability differs in different papers, as we are using paper 1 and paper 4 antibodies, and this can be affected by the regeneration solution, which is in pH around 2. In the case of paper 2, when using bioimprinting, we have 32 cycles for reusability. This is as this molecule is more rigid when we are using glutaraldehyde. And in the case of molecular imprinted polymers, we have 40 cycles. As this molecular imprinted polymer is a synthetic polymer and can be used for harsh conditions when regeneration is used. As a conclusions, the first conclusion that I have is a chip cleaning method was introduced, avoiding the use of piranha solution and the plasma cleaner. We have seen in bioimprinting that cross-reactivity was noticed, and however, this is significantly lower for the interactions. Gold nanoparticles has been seen that increase the surface area in the case of tyramine and gold nanoparticles, increasing the sensitivity in the sensor. Molecularly imprinted polymers can be used for more cycles, as this is a synthetic polymer, can support harsh conditions compared with macromolecules that are natural components. And the capacitive biosensor can be considered as a powerful tool for aflatoxin detection. Thank you for listening, and that's all.
Thank you, Alvaro. Now I will leave the word to the opponent. Professor Usun will give us an overview on the field. Please. Alvaro, please, can you remove your presentation, take off your presentation, please? Thank you.
Okay. Did you see my screen now?
Yes, 1 minute, please. Yes, Alvaro, please remove your presentation. Please stop sharing the screen. I think you need to stop sharing your screen. Otherwise, we cannot change presentations.
Javier?
Yes.
The presentation was removed.
Yes, but he needs to stop sharing the screen. It's removed, but it's necessary to stop sharing. Now it's good. Perfect.
It was
Yeah.
stopped.
Yeah. Thank you.
Thank you.
Now, did you see my screen?
Perfectly.
Yeah, okay. First of all, honestly, I'm really happy to be a member of this jury. When I reading this thesis, really enjoyed and excited. From my side, from my perspective, it is a very good thesis. In that thesis, already Alvaro summarized 4 papers produced. The thesis started with summarizing the motivation of this study because of toxicity of aflatoxin, in general mycotoxins, and summarize what type of mycotoxin and which fungal species produce these toxic materials and their effect on especially hepatotoxicity problem summarized in the thesis. Moreover, not only secondary metabolites of fungal species, but also biotransformed version of these mycotoxins also dangerous. After summarizing traditional methods used for determining amount of this contamination by giving small information about thin layer chromatography, capillary electrophoresis, enzyme-linked immunosorbent assay, and a high-performance liquid chromatography, and comparing their advantages and disadvantages. So the test continued with more recent studies like lateral flow sensors and the fluorescent polarization immunoassay summarized in the introduction part of the thesis. Because of thesis depend on biosensor, developing new generation biosensor, a small part including what is the biosensor, how generation changed day by day during the development, technological development, I mean, already summarized. And the main part of sensor and the main types of sensors already given in the thesis. Then the thesis focused on the specifically what used in the thesis in this study. The capacitive sensor summarized while emphasizing their important or advantages of capacitive sensor, main features of this sensor type. And already given Alvaro already summarized, shown this figure, the schematical view of sensor system used in this study, and how these sensorgrams mathematically operated already summarized in the thesis. Before starting papers published or prepared studies, some basic information already given in the thesis, characterization of cold nanoparticles, how capacitive behavior change by any modification applied on the surface, and some electrochemical characterization methods applied to characterize particles or polymers or materials used in the study already given, while emphasizing their advantages and comparing their features. Let me summarize from my perspective what Alvaro did. In first paper, they used self-assembled monolayer to functionalize the capacitive sensor surface. In here, 3 different molecular modification approach applied. The ultraldehyde assisted immunoglobulin G immobilization applied, EDC NHase reaction followed to immobilize protein, and the third method, electrochemical coating of tyramine on electrode surface applied. In first two examples, the carboxylic acid and aldehyde groups introduced to surface. So glutaraldehyde used as a spacer arm. In second way, carboxylic acid, and the last way, amino functional group used, decorated the surface used for antibody immobilization step. In here, different concentration range already studied, and very exciting limit of detection and the quantification values achieved in this part. At the end of first paper, Brazilian nut sample applied as a organic targeted materials to determine how much aflatoxin contamination added. Very low quantification level achieved, and this value already characterized, confirmed by ELISA measurement as well. And one of the main properties we are expecting any biosensor, reusability and the reproducibility of the data achieved. This paper almost 20-25 cycle applied, and the measurement, very precise measurement achieved in the first paper. In the second paper, the direction changed, and because of self-assembled monolayer, some disadvantages they have. Moreover, antibodies, according to the cost and the immobilization process, another approach, a bioimprinting approach applied in this study. In here, ovalbumin used as a bioimprinting substrate, and firstly denaturating, then in presence of aflatoxin cross-linking produced bioimprinted proteins. It has selective recognition cavities in itself. In here, Alvaro already summarized, there is very interesting differences between the non-imprinted and imprinted version of ovalbumin, very selective and linear response achieved by imprinting process. Meanwhile, very larger numbers of reproducibility data, reproducible data reported in this article. One of the main steps when we study with imprinted materials, selectivity, we have to sure how much selectivity we gained by imprinting process. As mentioned in the article, as reported in the article, the bioimprinted ovalbumin substrate selectively recognized the target aflatoxin species. Very larger working range and a very good limit of detection achieved in that study. In third paper, because of biological substrate, I mean the ovalbumin, resulted some unwished, unpleasant, non-specific interaction because of the other residues it has. That's the reason in third paper, Alvaro followed molecular imprinted polymers while applying electropolymerization, starting with the electropolymerizable monomers. In same direction, surface homogeneously coated, and voltogram, cyclic voltogram to show how much surface coating achieved by cyclic voltammetry. Then it's very large concentration range, and specifically recognition achieved by imprinting process in that study. As I said before, polymeric molecular imprinted polymer, specifically, the polymeric surface has a higher reproducibility because of they can contact harsh condition. They can applicable for recycling, more recycling numbers by this system. In third paper, in the first study, Alvaro used the antibody and then immobilized on gold surface, linear surface. Now it focused on increasing conductive layers by using the gold nanoparticles and immobilizing their recognition element on these nanoparticles, gold nanoparticles, I mean, and applying the counter-ion effect to form network formation, a net formation between these gold nanoparticles on electrode surface. In this study, you see in here, already Alvaro showed us very narrow size distribution achieved by these nanoparticles, gold nanoparticles, and proper concentration range. They achieved applicable response in a linear working range. In here, very important parameter I excited when I read, sodium chloride used as a counter ions to make an aggregation, to trigger the aggregation between gold nanoparticles. It's very effect on the performance of electrode as well. Let me skip this one. And as I said before, I'm really excited with this study. 4 papers produced during this study under this pandemic situation. 4 different approach to produce 4 excellent sensing performance with capacitive sensor. This is the last slide I want to share. As a conclusion, the Alvaro did very good work, and it's ready to defend himself.
Thank you very much for the presentation. Now we will start with the discussion section. Professor Usun, would you like to start with some questions or comment, please?
Yeah, thank you so much. I can continue. Actually, I took some notes when I read the thesis. Alvaro, are you ready? Can you see you? Alvaro?
Just a second, Martin, please.
Hello, Lockman. Yes, I am ready for the discussion, so we can start whenever you want.
Okay. Honestly, first of all, please accept my congrats. Very good work you did. I took some notes when I read your thesis. First of all, you did 4 different approaches to detect aflatoxin. Which one is the best, in your opinion, in your experience, according to your experience? Please consider not only LOD, LOQ values, but also user friendliness, cheap, cost, applicability to higher amount of samples. A few words, please.
I think that the best one, if we are considering the approaches that it has, and also the not using too many resources, could be the use of bioimprinting at the first, as this can be generating the specific pockets with specific pockets for the aflatoxin, and also this can be synthesized with another kind of for another kind of molecules. In the second one, I could put the molecular imprinted polymers for the electropolymerization, as we can get also pockets for this for a specific molecule. Yeah, then that could be.
Yeah, thank you. According to the result, I guess your answer should be MIP, not bioimprinting, because of some non-specific interaction occurred by other residues found in ovalbumin molecules. According to your result, the best result I saw from molecular imprinted one.
Yeah.
Paper 3, I mean.
Yes.
And secondly, actually in your thesis and your presentation, you mentioned the golden standard of aflatoxin detection is HPLC, high performance liquid chromatography. Did you have any information? Did you have any idea how this system works?
Yes.
All aflatoxin, 4 aflatoxin versions, all aflatoxin version can be detected by HPLC method easily or directly.
Yes, actually, in the case of HPLC, sorry, I will go through the. We are using for this time or a kind of a column with this the C18, that is the main one used for this aflatoxin when using HPLC, and is using also a kind of a fluorescence emission for the aflatoxin detection in the HPLC. And the main problem is the quenching of the effect of the native fluorescence that this has. So this column C18 is a reverse phase column to use, which is used specifically for, not specifically, but used for aflatoxin detection.
Actually, you mentioned that trained person needed for HPLC measurement. There is 2 reasons for this. Let me clarify or make some addition to your knowledge. The first one.
Could you repeat, please? I couldn't hear you.
Okay, my voice is now. It's good. Did you hear me?
Yeah. Yes.
Yeah. Let me say 2 important things, because in your thesis and in your presentation you mentioned that very accurate results and the fast result HPLC system supply, but trained person needed. There is 2 reasons for this one. The first one, and not for species aflatoxin B1, B2, G1, G2, not all of these these molecules fluorescence emission properties. You have to use some cobra cell to bromation of this aflatoxin to amplify their fluorescence intensity. That's the first reason. And the second one, why we need the trained person, you have to use immunosorbent assay, SPI, solid phase extraction procedure unit before inject your sample to HPLC system. Okay, let me continue with, you produced 4 different approaches. Why do you need other alternative methods others than immuno affinity system, like HPL system?
Sorry, I didn't understand the question.
In first paper, you already used antibodies as a recognition element.
Yes.
Then you changed the molecular imprinted versions. Why you why did you need to change your direction from antibody to polymeric synthetic materials?
Oh, yes. The first one, when we were realizing the measurement for antibodies, we have seen that this is a labile molecule where when we are using the regeneration solution for antibodies, this will be denatured in certain case. And then for that reason, the number of cycles that this is realizing will be lower. In the case of bioimprinting, we focused on this because this can be a more rigid molecule. When we denaturate, realize the formation of the pockets, then we go using to the glutaraldehyde, and then with the reduction with borohydrate. And then for this reason, this bioimprinted protein will be more rigid and can be used more times. So this is the reason for this. And in the case of molecularly imprinted polymers, as this is a synthetic polymer, then this can resist harsh conditions. As we are changing we are realizing the regeneration from a pH around about 9, so that is really high.
Related to this question, do you have any idea the price of aflatoxin antibodies relatively higher than other antibodies? Why?
What do you mean about the cost, or?
Yes, cost. Why the cost of a specific antibody against the aflatoxin higher than the others?
As this is this antibody is a monoclonal antibody, then this will need several processes in order to produce it with cells. And in the case
you can compare. Sorry, you can compare the monoclonal.
Okay, yeah, but in the case of bioimprinting, we are using a protein which is easy to obtain. So this will be reduce the cost in order to use it with different molecules and simulate the behavior of an antibody.
Let me interrupt. I mean that you have aflatoxin antibody, you have albumin antibody, anti-albumin antibody. The price of aflatoxin antibody is higher than price of albumin antibody. Why? Do you have an idea?
Just for the production.
Because, let me help you, because this aflatoxin is small molecule. They cannot make a immunogenic activity on bacteria, on animal. Yes. Therefore, you have to use some haptens, carrier molecules. First, you immobilize your molecules, aflatoxin, these haptens, then give these larger molecules to system to produce monoclonal antibodies. Oh, yes. That's the reason extra step make higher cost.
Yes.
Here, in antibody immobilization procedure, you have 3 different surface functional groups: aldehyde, carboxylic acid, and the amino functional groups.
Please, 1 minute, please. We are going to configure something here. Please, just
okay. Okay.
I'm sorry, please. We are adjusting some.
Yeah, no problem.
Alvaro cannot listen very well, and we are making some adjustments, please.
Yeah, no problem.
El otro más, ponte el otro.
Hello.
Hello? There is echo.
Sorry. Now,
Yes, still there is echo. Please close to other microphone.
hello. Now,
Yeah, there is echo. I guess there is
Hello?
two computers there. Say again?
hello. No.
Yeah, it's better.
Yes. No. Still. Now, yes. Can you hear me?
Yeah, it's not.
No interference.
Yeah. At least for me, it's good. No problem.
No, I cannot hear you.
Oh, can you hear me now?
No funciona. No seguiremos nomás con lo que está. No, está peor. Okay, so we are going to just continue like where we started.
Okay, don't worry. I will finish soon. I will finish soon. Don't worry. Yeah, during antibody immobilization step, you have three different surface groups: aldehyde from glutaraldehyde, carboxylic acid from thioconic acid, and amino functional from tyramine. Which one is the more useful for immobilized antibody? In other words, did you have any hint or any problem, any troubleshooting idea you have? Which functional group is easier?
The aldehyde group, as this will be interact with the lysine residues of the antibody directly. In the second time could be the dioctic acid, but this need to have the activation with EDC in order to react with the antibody. And the third could be the tyramine. But
okay.
I have to say something about here in tyramine. We are using this over these tyramine gold nanoparticles too. And so in the case of tyramine electropolymerization, the antibody will be adsorbed over the gold nanoparticle.
Interesting. Two questions left. The one is that about the bioimprinting. When you present your speech, also mentioned in your thesis, you choose ovalbumin because you already tried albumin, but it has some hydrophobic residues. Therefore, you change direction on ovalbumin. What is the main criteria to choose for choosing the best bioimprinting substrate? I mean, a protein.
Yes, in the first case I was using albumin, but I changed this part as this has more hydrophobic residues of amino acids. So when we are realizing the regeneration in the capacitive sensor, this is difficult to release, and we are going to use more harsh conditions in this. But even so, we are not getting a good regeneration after the ovalbumin is used. Yes, and after that, as we have seen that ovalbumin has more hydrophilic residues, then it's easier to release this aflatoxin from the surface of the printed protein.
Okay, let me ask this question in other words. Why you didn't use the insulin? You can use the insulin for bioimprinting process. I asked the main criteria for choosing the proper protein during a bioimprinting process. You already used the ovalbumin. The question is that, can you use insulin, other protein or hormone, polypeptide, shortly? Can you use this one? shorter molecule, it's getting lower non-specific interaction, something like that.
Yes, if we have a good interaction between this insulin or another protein, troponin or so on, then we can follow the same steps in order to create these pockets on the surface. But we have to see also if this protein has the characteristics which are easy release of the aflatoxin when we are using a regeneration solution. So I think that this will be the main topic of this, choosing the protein. If we have the groups that can be facilitate or give us the easiness for the release of this aflatoxin. So must be realizing the evaluation of these different proteins that we can use.
Actually, when we choose the substrate protein, in your case, O1B, we focus on monopolypeptide structure it should have. The insulin has two polypeptides that make your, the main criteria is that it's very stable single polypeptides we have to choose as a substrate protein. Okay, the last thing that, did you vary flow rate during capacitive sensor, flow rate and temperature? There are some effect on your detection limits or your signal sensorgram, I mean.
Actually, we are not. We are using just the temperature of the lab, so we were not trying with different temperatures. But it's known that when we are using temperatures, then this diffuse layer will the molecules who are how to say, it's in the outer Helmholtz plane, we diffuse to the bulk surface when we are using higher temperatures.
The double layer formation energy will change its effect on your performance as well. Yes. What about the flow rate?
This flow rate can affect when the antigen will bind to the antibody of the biorecognition element. In order for the flow will affect the state in order to bind these two molecules. Maybe the flow rate, if this is too high, then the molecules will pass directly and then will not have this kind of reaction between the antibody and the aflatoxin.
Yeah, shortly, antigen needs enough rotation time to interact correctly with your surface. Thank you. Javier, it's my question already finished.
Thank you very much for the interesting discussion. Now I will leave the word to the committee members who would like to start with questions or comments. We can probably start from the committee members sitting here in the room.
Yes, I can start with the questions. Many thanks for your presentation. Can you hear me?
Yes, I can hear you.
Okay, so from the technical point of view, everything is fine. Alvaro, congratulations for your work and your effort to persuade on this important topic, detecting the alpha-toxin. I collect a number of questions here, and I would not like to have them only as a question, but also as a basis for a dialogue, a discussion. I would refer first of all to page 42 in your dissertation. You also mentioned this equation with the elements of the capacitor at the interface. And you are mentioning also in the publications about insulating properties at the electrodes, which are extremely important. And I want to to differentiate in which sense insulation we can understand it, and what is the importance of insulation. Can you start discussing about, and then I might return with further comments?
Okay. Yes, we have to consider here that when we are using a capacitive biosensor, this is a non-Faradic process. And then we need to create an ideal polarized electrode, which is given when these self-assembled monolayer are attached to the electrode surface. So in this case, I think that this is the answer that you have. You need to know about this for the insulation.
So when you refer to insulation, you mention resistance. So yes. Let's point it differently. Are you accustomed with impedance spectroscopy?
This can be related. It has been seen that also using impedance can be measured the capacitance, which is in the case of impedance, we have the, how to say this? Actually, the impedance will be the resistance that is happening in the process. And this will be related contrary to the capacitance in this case.
So the impedance, it's defined or it has a real component, which is a resistor-like component, and imaginary component, which is a capacitive component. If you want an interface to be isolated, you increase the real resistance of the system, but not the to increase the charge diffusion capacitance. I want just to understand differentiation between this aspect, what it means insulating, increasing the resistance of the interface, and your wish to increase the capacitance of the electrode.
The capacitance will be increased when we are using the self-assembled monolayer, as this must be as high as possible. As the less, as has been seen in the double layer, the less capacitance will dominate the total capacitance of this. So we need to increase the capacitance.
So to return to definition of capacitance, how you define capacitance?
It's the, how can I define it? It's an effect caused by the double layer when we have a polarized two different kind of charges between the measurement system, and
at the time when you are measuring the change in the capacitance, you are measuring the exchange of the ions at the capacitance, yes, at the interface.
Yes, yes, yes.
And you want to make it as sensitive for your detection molecule and less sensitive for the layers that you have at the electrode. So the electrode will not participate per se, but only your detection molecule.
Yes.
So you don't have to have an insulated electrode. You want to have an sensitive electrode, but which does not exchange ions per se, but only will let your detected molecule to exchange these ions by its presence.
Yes. Actually, when we are realizing the measurement of the capacitive sensor, when the analyte molecule will bind to the antibody, then the the layer will diffuse. And then here will be registered the change in capacitance when this layer will be diffused. So we are talking about the diffuse layer that is moving.
And you still want to keep your electrodes sensitive enough to measure that change of ions at the interface. So you don't want to highly isolate it. So insulating, it's not a correct term when you want to measure the capacitance. You want to keep the resistance low, that the electrode is sensitive, but not, this is my point. This was the debate about this insulation, yes?
Okay.
You are referring in all this dissertation, you use a certain method of detection, and it's named using current pulse method, yes. But was just mentioned as a reference where was addressed first time, but was never discussed or presented in your publication. Can you present it or describe it to us?
Yes, here we, sorry, we'll just look for some. The current pulse method is based on this situation. We are using, when, okay, the system was used in the current pulse, when at the first instance, current is applied on the capacitor. Then when this current is charging the circuit, then the current will maintain for a certain time. For example, in here is using plus 10 microcoulombs, I think, yeah, microamperes. Yes, they are using 10 microamperes for the first time, and this is sending a constant current pulse to the working electrode, and then the potential will be reach a predetermined value, and this will be given as a slope that is going through to the system. Then once more, this current is going to zero, and then a negative current is applied as the same as the first one, but minus 10 microamperes. And these are stayed by 2 times that the first current that was given. And then once more is stopped, the current goes to 0 level, and then once more is given a third current. When this third current results in then is also going for the same time that the first one. So the current pulse goes first in a positive range, then a negative range, and once more to the positive range. And this will be a cycle for this current pulse method.
Can you comment at which frequency you change the current, or what is the duration of a pulse?
No, actually, I'm not sure about that.
Okay. Your thesis has the name optimization of detection of alpha-toxin. Are you sure that the frequency of your detection methods, this current pulse method, it's optimized for all these systems that you studied? Because an interface will have an optimum frequency at which you can detect with higher sensitivity. Did you look to optimize in this sense the detection method?
No, actually, that values was standardized for the system directly, and this is made by Erlandson and co-workers. So they realized all the standardization for this capacitive sensor. I didn't standardize that part.
Do you think that it should have been also optimized for your setup, or each of these designs that you had at the interface, or they are ideal for all interfaces?
Actually, many people has been working with this system, and there was the different methods that they were using for in the immobilization for these molecules and so on has had really nice results in all cases using the parameters which are stated for this capacitive sensor in the current pulse method.
Okay, thank you. In the paper, in the last paper, number 4, where you used sodium chloride to aggregate the particles, to bring them closer to each other, you obtain an optimum sensitivity for detection for a concentration, the 250 millimolar sodium chloride. Can you discuss why necessarily you get the highest sensitivity for that particular aggregation, and why not for 500? Why it is a maximum there?
Yes, actually the detection using 500 millimolar, 250 millimolar, and 5 millimolar of sodium chloride has the same linear range in all the cases. But we focused on this 250 millimolar as the percentage of antibody absorption over this gold nanoparticles is the highest one with 57.7%. For this reason, we used this 250 millimolar as we had more absorption of the antibody.
The absorption of the antibody, it's different indeed. You have an optimum for this 250, but the sensitivity, it's 5 times higher in comparison with the other 2 methods. So do you think that will explain only the absorption of antibodies, or also the density of the particles might play a role?
Actually, yes, the density of the particles will play here, as just the antibody is the reference that we have to know which one of these net formation has the largest surface area in order to be able to use it with the antibody in this case.
So at the time when you use a 500 millimolar sodium chloride, you might create such a dense particle aggregates that they are not any longer contributing to sensing principle of your.
According to the results from the absorption of this antibody, will be related the percentage of this absorption. As we have, if we have a more a large surface given by these gold nanoparticles, then more antibodies will be attached over this gold surface.
Do you expect that the gold nanoparticles, it's a monolayer of gold nanoparticles, or there are multiple nanoparticles in this net which are at a certain level limiting the diffusion of ion cations in the system?
Yeah, these are multi-layers that will be forming here, as the cross-linking will be between the all gold nanoparticles that is present in this. So the antibodies will be covering over the gold nanoparticles.
And one last comment. It's you mentioned a very important parameter of alpha toxin or property of them, that they are binding to the DNA. They are kind of a DNA intercalator.
Yes, actually, these are forming adducts in the DNA.
Mm-hmm.
If we see in this sequence, but this is specific for guanine residues, which is forming this adduct. So this will alter the conformation of the DNA, and this DNA will go to the mutation. And this after the accumulation of more mutations did by this aflatoxin, then this can trigger toxicity for the liver and liver going to the cancer production according to this.
So my comment, it goes in an idea of a possible detection mode in the capacitive with the capacitive principle, where you immobilize on the electrode short double-stranded DNA rich in guanine, which will accept and accumulate the alpha toxin directly on the electrode, and you will see capacitive change by intercalation of this one on the DNA, on the electrode. So this might be also a detection principle.
Yes, maybe can be realized also.
It was for other molecules, such as sensors are existing. Therefore, I'm just suggesting to you as a possible continuation.
Yes, will be. It's a nice. Yeah, thank you.
Okay, I stop here for the moment.
Thank you. I will leave the word to Dr. Jaime Castillo León.
Thank you. Alvaro, I would like to continue the discussion more or less in the same line that Leonard, talking about the optimization. One important component of your system was the self-assembled monolayer, since it was used in several of the experiments you did. Did you do some other validation of the self-assembled monolayer to evaluate how good was the self-assembled monolayer deposited on the electrode?
Actually, we were working just with this thiourea. We used another kind of molecules, but I don't remember the name now. But it was also Mercapto molecules. But we at the end of this analysis for this capacitive sensing, we just focused on thiourea and thiotic acid. And the main focus for using this thiourea or thiotic acid, it was in order to have the reagents when I will be here in Bolivia, as we cannot reach these reagents easily. So that was the reason why it was focused on more simple molecules to use it on the biosensor.
And how did you check the quality of this self-assembled monolayer? How good was created on the surface of the electrode?
We were using cyclic voltammetry, but this was used when we were in Sweden. So we standardized the method in Sweden, and then we came here to Bolivia, and we started to use the standardized methods in order to realize the detection in the biosensor.
Okay, and let's say you created a terrible self-assembled monolayer. So what will you expect the cyclic voltammogram? How it will look then?
Sorry?
If you say you were using cyclic voltammetry to evaluate the quality of the self-assembled monolayer.
Yes.
So if this self-assembled monolayer has a really bad shape, what will you expect in the cyclic voltammogram? How it will look?
This can be given by the anodic peak current or cathodic peak current, where this will differentiate or maybe appear in another kind of different form, like undulations or something like that in the cyclic voltammetry, where this is not well used.
Okay, and what kind of defects could you get on a self-assembled monolayer, for instance?
No, when I was using, I didn't have any kind of effects that was different for the normal cyclic voltammetry that we had.
And do you know any other ways to evaluate the quality of the self-assembled monolayer apart from cyclic voltammetry?
Yes, maybe we can use maybe you can use amperometry also to evaluate in order to see the exchange of the electrons that is happening in this layer. So we are going to see if we have the a reduction current or an oxidation current and so on.
It's also good to evaluate other techniques separately from electrochemistry. For instance, you could use AFM to give you an idea of how is the surface, but yeah. Then going to the gold nanoparticles, I saw that it was really useful because increased the surface area of your sensor. Did you optimize these gold nanoparticles, or what was the size that you obtained initially? Did you characterize that?
We were using there are many ways to prepare these gold nanoparticles. And then we use a specific method in order to have nanoparticles in order to nanometers, in order more or less 100 nanometers, just for have the one size of this one. So after using this, then we use the concentrations of salt in order to really decrease the repulsion from these gold nanoparticles in order to realize the net formation.
So it was you who fabricate these particles? Or?
The gold nanoparticles, yes, I did it. We realized the fabrication of the gold nanoparticles.
And did you measure the size, or what type of size did you obtain with your methods?
It's around 100, I think. I'm sorry, I'm not sure about the exact size of this, but it's in order less than 100 nanometers.
Okay. And did you make a comparison? How much was the increase in the surface area? Because I was interested to see that in the article, but I couldn't find, comparing with the clean electrode, the flat electrode, how much was the increase in the surface area when you put the gold nanoparticles?
I haven't did the direct comparison, the comparison for this, the flat one, just using, the antibodies or something like that. We were just using the direct to the gold nanoparticles in order to create this formation of the net.
Yeah, but that could be also something good to evaluate to see if maybe you have a space to change the size of the particles and even increase further the surface area. And do you think there is a limit of how much you can reduce the size before you start to see saturation or not change at all? Or also, do you think the size of the nanoparticle will influence how much antibody you can attach?
We just tried using this method for the gold nanoparticles with almost the same size as I told you before. So we haven't evaluated another kind of gold nanoparticles which are bigger in size, because we can synthesize bigger or smaller. So, but we haven't do this.
But do you expect that the antibody attachment will start to be affected at some point if you start changing the size of these nanoparticles?
Yes, actually, yes. This could be changed, the percentage of absorption that could have in this surface of the gold nanoparticles, depending if these are bigger or smaller, as we are going to have more. The surface area of this gold electrode will change depending on the size of this one.
Okay. And then some final questions regarding the use of the antibodies. What other challenges do you think you normally have when you use antibodies, immobilization of antibodies? Did you check, for instance, the orientation was always the same of the antibodies you immobilize?
No, we haven't seen the orientation of the antibodies.
And do you think that orientation could affect the sensitivity of your system?
Yes, also can affect us. If we don't have the specific recognition part from the antibody in the upper free in the solution, then this aflatoxin will not attach or bind to the antibody. So this is also one effect that is not good for the measurement in the capacitive sensor.
Good. And regarding the interferences that you evaluated, what was the method or the principle to avoid that these interferences generate an extra signal in your system? How did you avoid these interferences?
What kind of interference? What you mean?
I think in one of your articles you have you evaluate some compounds that could be interference in the analysis. Or
in the case of bioimprinting.
Yeah, in general, how do you avoid interferences in the
just for the when we are using, for example, bioimprinting, we have non-specific interaction with other molecules. So this will be seen when we are measuring the capacitance. So the decrease in capacitance will appear for these molecules, showing us that there is an unspecific interaction. Always when we are using a standard molecule, of course, that is pure.
Okay. And then the final question, you say that one advantage of biosensing or electrochemical biosensor could be to simplify the analysis. So in case of the sensors you development, if you want to measure this toxin in a real sample, will you need to do some pre-treatment to your sample, or you could measure directly?
In this case, as we have the Brazilian nuts, we just need to grind these nuts with methanol in order to release the aflatoxins, and then this will be just a simple filtration, and this filtration can be used directly. So it's not necessary to realize many steps in order to purify the aflatoxin or so on. And we understand that in this complex matrix from the Brazilian nuts will be also other components, but this is not affecting in the sensing, as this is a specific molecule that is used.
Good, thanks. Those are all my questions for the moment.
Thank you. Now I will give the word to Associate Professor Peter Spegel, who is participating via Zoom.
Yeah, hello everyone. Can you hear me?
Yes.
Super. So I would first like to start by saying that it was for me very interesting to read the thesis, because I do not really have any experience in sensors. But I am an analytical chemist, so I will instead ask some questions about quality aspects of the technology and the data that you generate. So you talk in your thesis, and also in the papers, you have two words that you use quite often, and that is selectivity and specificity. And you seem to use them quite interchangeable. Do you know what the difference is
between
specificity and selectivity from an analytical point of view, as you are measuring things here?
Specificity will be how do I say that this the biorecognition element can just recognize this target molecule and no other ones. Yeah, okay, and the sensitivity will be
selectivity.
Selectivity.
Yeah.
Oh, sorry. Selectivity will be just to differentiate between other molecules and that can be present between in this solution, and there is no interaction for this one.
Yeah, so they are somewhat different. So I mean, a method may have different levels of selectivity, but a method may be specific or it may be not specific. So from an analytical point of view, a method that is specific has 100% selectivity. So then it will be either specific or it will not be specific. And I think that is how it's often used in, for instance, validation, when you test your method, whether it's fit for purpose or not. So just then looking into UPAC. So UPAC say that a biosensor is capable of providing specific analytical information. Do you think the UPAC definition is good?
Sorry, what technician?
The definition by UPAC you mentioned on your presentation, stating that a biosensor is a specific analytical technique. Is that a good definition, do you think?
I think yes. I think that is the correct definition, because we are having this. Sorry, I will go to the.
Because I mean, are there any biosensors that are 100% selective? That is, that they are specific. I would say that probably, I mean, yeah, according to UPAC, I guess there will be not many biosensors around. I think they should change their definition, UPAC. So maybe you can help out there.
Okay.
Yeah. So let's switch a little bit to molecular imprinted polymers, because I spent 5 years synthesizing MIPS when I did my PhD, and that was more than 15 years ago. So I'm really happy to see that the MIPS are still around. So you mentioned, for instance, that they are specific, but we discussed that. I would say that they are not really specific. They show some selectivity. But I think the main problem with MIPS is that they have some problems. Can you mention some problems that you have with a molecular imprinted polymer?
This will the interaction from this imprinted MIPS will be depending on the kind of groups that these monomers it has. So when we are choosing one or the monomers for this imprinted polymer, then we need to know what kind of groups we have, and then what kind of interactions can give us with the target molecule. So this is the main inconvenience. We have to choose which kind of interactions we are going to have in the system.
Yeah, and that is of course extremely important, and I will come back to that shortly. But do you think that there are in a polymer that in which you do imprints, are there two imprints that are identical?
I think that there is no identical, because the aflatoxins will not just in the same position all the time. Will be in different positions, or maybe inside the polymer. So we are not going to have the same configuration for each pocket that we are generating in the molecular imprinted polymer.
Yeah. So what? Because I know in chromatography that I was working in, this was a big problem. And what are the problems with that if you consider a sensor approach? Are there any problems? Now you have to teach me, because I don't know.
Another problem from this. As has been seen in the imprinted polymers, we have some the pockets forming in this surface, but maybe we can have also another pockets that are inside the molecular imprinted polymers, that where the target analyte can attach to this, but this will not exert any kind of interaction in the capacitive system. And then this aflatoxin will be just measured when these pockets are on the surface from this molecular imprinted polymer, in order to move the diffuse layer and to generate this change in capacitance.
Yeah, I think that's a good thing, because you don't have the issue with the distance there. And you mentioned interactions. So what type of interactions do you have between your analyte and the polymer? What are the interactions between that are governing the imprints?
As we can see with the monomer that we are using, there will be just hydrophobic interactions between the aflatoxin and this monomer, or the polymer when it's formed.
Yeah. And how is that impacted by, because you're doing the polymerization in methanol and water? Have you studied that?
Yes, it has been seen in many articles when this electropolymerization is realized, it's necessary to use alkaline solutions, as these alkaline solutions will realize the self-growth of the layers. And this means that the one polymer will be formed just for example, 7 layers. And if you are still generating this cyclic voltammetry for electropolymerization, then there no more layers will be formed over this one. So this is the main effect when we are using the alkaline solutions.
Okay, yeah. But would it be better if you skip the methanol? Would that be possible?
This will be just in order to make it more soluble, the tyramine.
Okay. Yeah. And then I was not 100% certain about what the polymerization you do, but are there any cross links in there, or is it just linear polymers?
There will be some interactions between this. This is the polymer, such as where this is in a line, and there is also some interactions from hydrogens between these two molecules of this mercaptobenzimidazole. So hydrogen bonds will be found also between these two ones.
Will they, if you have your sample in water, will they exist?
Yeah, it can also interact with the water, just in order to form this hydrogen bonds. Yes, so for this part, for this part even can interact in a hydrophilic way also with the groups present in the aflatoxin.
But I guess maybe if you do the polymerization in water, in very aqueous environments, they should be quite strong, weak, I guess. Yes. Those interactions.
Yes.
Yeah. So I'm wondering, because in the old days when I worked on this, we often used highly cross-linked polymers, 50% cross-linking, which is quite extreme, to be able to have imprints that's sort of survived, because you didn't want the polymer chains to move around, because then you lost all the recognition. So that's why I was asking how this really works. Do you think it's possible that you electropolymerize the toxin together with the monomers? That's I don't know anything about this electropolymerization, but do you think that could be a possibility?
To realize the electropolymerization, how exactly do you mean?
Yeah, I mean, if the template molecule, your alpha toxin, if that is in the environment you create when you do the electropolymerization, do you think it may become bond to this polymer chains?
To realize direct interactions?
Yeah, I mean covalently.
Covalent. It could be some interactions between this aflatoxin with the amine group that is present in this monomer. Could be some kind of interaction, but I am not sure if this could be a covalent bond when we are realizing the electropolymerization.
Yeah, I don't have any idea about that. I'm just a little bit curious, because the system is so different from what was used in the old days, where you had a lot of cross-linking and creating selectivity based on sort of hydrogen or polar interactions in hydrophobic environments and so on. It's completely opposite this system. So it's quite interesting, I think, that it seemed to work.
Yeah, it works.
But one final thing here, and that is because also if you do also what I know from the past is that when you do a polymerization and if you add a template, that may actually impact the morphology of the polymer that you create, because you change the sort of chemical environment during polymerization in some way. And actually I have a lot of experience, and I've seen in many studies that when you add the template, you may actually create sort of more fluffy polymer structures with bigger surface areas. You may change porosity and other things. So I'm just wondering, how would you test that this is not occurring here and that this has some impact on what you observe later on when you compare the non-imprinted with the imprinted?
In this case, we were just measuring the capacitance in the system using the aflatoxin for the imprinted and the non-imprinted. As we have seen in the figure that I shown before, there was not interaction in the non-imprinted polymer for the aflatoxin, so there is not any kind of interactions that can happen with this non-imprinted polymer. Yeah.
And that could not be due to that the polymer is very different in presence of templates. I guess it should not. Yeah, but I think it's fascinating. It's different, and it as you say, it seemed to work. I like in your summary you discuss different analytical techniques to assess these toxins. And do you know which technique is used in the pharmaceutical industry, for instance?
The most used is the HPLC.
With what detector?
Fluorescence detector.
Well, I think at least in the pharmaceutical industry around here, I think it's a lot of LCMS that is used.
Oh, okay.
If you compare your sensor to a mass spectrometer, what would you say?
Oof. I'm not sure how to answer this.
Yeah. Selectivity, yes. Detection limits.
Yes, but
yeah, it's a difficult question.
Yes.
Let's see. Then I also have one last sort of statistical question, and that is in paper 1, you present a 3-level full factorial design. So you examined all combinations of 2 variables at 3 levels. And I couldn't really follow. You selected one condition that seemed to be optimal. How did you evaluate the design, and how did you come up with the optimal condition?
These optimal conditions were first, when we are using the phosphate buffer, then we have to know that these have different pKa's and pKb's. So in this sense, we are using where the pK, one of this pK is present. So for this case, we have a 7.2, that is 1 pK. So we can go around this in order to have a buffer in order to avoid different we need to have this buffer in order to avoid these different situations where the pH will increase or decrease. dramatically. So this is not good for the assay.
I was
And in the
mainly
case
thinking of what is the advantage of using a full factorial approach as compared to just testing some random conditions?
How do you mean that?
Because I think it's table 1. Let's see, so I don't get this wrong. Because you have in table 1, you have a factorial design for selection of regeneration buffer and running buffer. So I guess you tested a number of different conditions here. And so what is the advantage of doing this way and not just testing something randomly? Or doing things one by one?
Yeah, as we are going to see also the changes that we are going to have, we need to, in order to realize the setup for the capacitive sensor, we need to have these baselines, and these baselines will help us to have reliable results in the capacitive sensor. So if we don't have these reliable conditions, then we are not going to have good results. In the case when we are realizing the regeneration, then we need to have some baseline when we are realizing the regeneration. And in the second cycle, this must be reproducible. So this will be all the same in order to have that we are working in a good way for this capacitive sensor.
Yeah. Good. Thanks a lot, and thanks for letting me read your book and listening to the presentation. I have learned a lot. Thank you.
Thank you.
Thank you. Now I will leave the word to Dr. Sylvester Gaspar, who is also participating via Zoom. Please.
Okay, so can everybody hear me?
Yes.
Great. So I prepared a number of 12 questions. I will skip most of them, and I will take the time to highlight 2 positive aspects of your thesis, and then I will ask you maybe 3-4 questions, okay? Because the most probable outcome of this event is that you will get this PhD degree, and I just kind of want to give some motivation for that. So I think the most important positive aspects of this thesis is that, first of all, it is focused on an important problem. So about, according to some sources, 25% of the global food crop production is contaminated with mycotoxin. So we really need a sensor which is simple and easy to use. And that would be very helpful, no question about it. And then the second positive aspect of Alvaro's thesis is that this thesis really tries to perfect things, to make this biosensor better and better. And you might ask, why is that good? So that is good because the field of biosensors has a bad feature. It puts forward a lot of concepts, but it doesn't take the time to perfect them, to optimize them to the point that the concepts are really useful. So the fact that you try to go through these recognition elements, you try to build these different sensors in order to make it better and better is a positive aspect for sure. Okay, let's move to the questions now. And the first question is related to a graph, which is shown in page 25. So there you have a plot which shows the evolution of the aflatoxin concentration in time for a Brazilian nut sample which was artificially contaminated with the fungi. And these graphs goes up to hundreds of picograms per gram. And this level is significantly lower than what is admitted as admitted levels of mycotoxins in crops and food products. And my question is, what experimental condition was missing? So why this artificial contamination didn't produce a lot of aflatoxin?
Do you say artificial?
So if I understood correctly, figure 3, page 25.
Yes.
So you contaminated a sample of Brazilian nuts with fungi.
Yes.
And then you follow the evolution, the increase of aflatoxin concentration. Okay.
Yes.
And this concentration stayed very low. So, and my question is why? So what is going on in real life? So why food crop gets contaminated and producing contaminated with such high concentrations of aflatoxins, but not in this experiment? It didn't happen. Why? So what is different?
Okay. When we were measuring here the concentration of the aflatoxins, we were realizing dilutions that maybe I haven't put in here. So the concentration, when we are realizing the capacitive sensor, we have a linear range that we can measure these concentrations. If we are going up to the linear range, then these concentrations will be not useful for us. In that sense, the concentrations who are created in here, it was higher, but I haven't, yeah, that's the point, I haven't put in here. So the thing it was, in order to know that the production, just this figure is showing the production of the aflatoxins during the time. So during the time, the maximum production of aflatoxins for a mold will be around 12 days, 12 to 14 days. So that will be the top of the production for mycotoxins. And after these days, there will be not more production for this aflatoxin.
Okay, so what you're saying is that you meant this graph to identify the time when the concentration of the aflatoxin reaches its maximum.
Yes.
But there were dilutions involved. So
yes.
The concentration of aflatoxin in the sample was different. Okay.
Yes, in order to get inside the linear range. Maybe that's not described in here. So I forgot it.
Okay.
But,
yeah, the text associated to this graph gives the impression that this is what happened in the sample. Okay. Then another question is somehow related to what Leonard was trying to say about the difference, what is insulating, and if you need something insulating or not. So you have gold electrodes, which you modify with this thioctic acid. And you have shown that this forms a monolayer which blocks very well hexacyanoferrite. And I expect that thiourea, you didn't show results about this, but I expect that the voltamograms were showing that this molecule is not blocking so pronouncedly the surface. Is that correct or not?
You mean that the thiourea is not blocking correctly to the is not well correct used for insulation for this electrode?
No, thiourea is a small, different molecule. So its ability to block the gold is not as good as that of the thioctic acid.
Yes.
Didn't you observe that? I expect that you have observed that if you perform cyclic voltammetry.
Yes, actually, yes, we realized the cyclic voltammetry for this, for thiourea, thioctic acid, and the insulation for this thiourea is also similar for the thioctic acid. So the size for this is not saying that this insulation is not happening on the electrode. It's happening in the insulation, but it's almost the same figure that we have for this cyclic voltammetry between thioctic acid or using thiourea.
Okay, that's a surprise to me because thiourea has no structure which would recommend this molecule to assemble and to block surface. So, okay. Then another.
Coming back to that question, we are considering also that this is of course a small molecule, but after this after immobilizing this thiourea, we are using also glutaraldehyde, who is going to be bigger this molecule. So every time that we are introducing new molecules or layers in this, then the isolation will be higher for the electrode.
Okay. Then let's move on to, I think, paper 2, yes, which uses bioimprinting as a way to make a sensor. So there is something interesting for me, because you use dialysis to remove the template from this bioimprinted structure. And you did dialysis in a diluted buffer. So apparently, using, I think, 10 millimolar phosphate buffer lets you remove the template from the bioimprint. On the other hand, when you move to the bioanalysis, this is your carrier. So you inject this, you inject the aflatoxin in this solution, and still it binds to the surface. So apparently the same buffer helps you to remove the template and then to add it. So can you explain this, why something like this could happen?
Yes, in the case when we are realizing the dialysis, we are letting here for overnight. So we are letting around 12 hours, 24 hours in order to get the release of this. This will be not just the injection of the buffer sample and then the release of the aflatoxin will occur. So this will attach to the imprinted protein, but in the dialysis, as we know, is for the concentration gradient that we are going to have between this semi-permeable membrane. So this is where this aflatoxin will be going to to diffuse the concentration. So for this reason, this will be released. But this can interact with the bioimprinted protein with the specific sites that we have in the bioimprinted protein.
So you see this binding as an equilibrium process, and then you say that the fact that dialysis is made in a large volume, you kind of remove slowly the template. That might be the case.
Yes, it's slowly the remotion from this aflatoxin.
Okay, and then you had also a discussion with the opponent about which biorecognition element you would put first, which is second, and things like this. And it turned out that you would put the bioimprinting as the first place and so on. And a reason for that is that you succeeded to do a higher number of measurements with that type of biosensor. And in general, you tend to explain this higher number of measurements by the stability of your biorecognition element. And you say that, okay, I succeeded to do only 25 measurements with the antibody modified electrodes because my antibody is unstable. But on the other hand, there is an interface which you have modified. There can be distortion of that in time. So how can you be sure that this instability you notice or the stability you notice is due to the stability of the biorecognition element and nothing else?
This was noticed when, after realizing all the experiments, then we have the repeatability for in different number of cycles for each molecule. I mean, 25 for antibodies, 32 for bioimprinting, and 40 for molecular imprinted polymers. This is one of the ways to know how the molecule is affected. But we know also that when we are using harsh conditions, we can also release in certain time the the self-assembled monolayer from this electrode, as the regeneration is a harsh condition. So this can break this covalent bond between the sulfide and the gold, and then will be more pinholes in the electrode. So the changing capacitance will be really randomly and maybe rising up. That is the normal case when this is measured.
Okay, so we have an agreement on that. Instability or stability is not only of the biomolecule or biorecognition element, is of the whole system. So that things can happen in parallel with this denaturation of the antibody and things like this. So final and an easy question is about your sample preparation. So I expect that these fungi grows on the surface of the nuts, for example.
Yeah.
And I expect that they generate and they contaminate the surface of the nuts. So I was wondering, why did you decide to grind the nuts? Did you try just to wash their surface off with ethanol and use that sample? Or did you investigate a little bit if this sample preparation is the best for your analysis?
Is the most recommended one, as this the force that is using for this grinding will release the aflatoxins that is on the surface of the Brazilian nut. So in this case, if this aflatoxin is well attached on the surface of this Brazilian nut, then this will need some force in order to be released, as we are just pouring methanol in order to release the aflatoxin, or not, we will not have all the aflatoxin released from this surface. So this is just to realize a homogenized mixture, and then having the aflatoxin released on the solvent, that is methanol in this case.
Okay. Mm-hmm. So I had a number of other questions, but I think I'm satisfied with how you answered the 4 or 5 questions I have put. So that's all from me. Thanks a lot.
Thank you.
Thank you. Carla, please ask if the audience in Bolivia has any questions.
Thank you. In the same way, is there any question from the audience here in La Paz? No questions, Javier.
Okay, in that case, I would like to announce that the session is ended. Now the opponent and the committee members will hold a meeting in a separate room. They will come back after reaching the session.
Thank you. Thank you very much.
So I suggest the following, that the opponent and the committee members on link, I will create a breakout room, and the people in Bolivia and the respondent can stay in this main room, and the committee will then come back to this main room in a certain amount of time, I guess take 10-15 minutes. So I will create this breakout room now, and I will assign the people to this.
It's okay, thank you.
Thank you.
Van a calificar ahora ellos. Y luego
Yeah.
van a volver y nos van a decir cómo ha ido la revolcada.
So where is Peto? Ah, they left. Okay, they left. So, okay, we will do like this instead, because the 2 committee members, they will join. So I will end this session here for a short while, Carla, So in 10, 15 minutes, please go back to the Zoom link. Can you confirm?
Yes, perfect, Martin. Okay.
In 10, 15 minutes, please come back to the Zoom because I have to end this.
Perfect.
Thank
It's
you.
okay. Thank you.
Thank you.